Okay, this is video lesson for lesson 1.2, which is Exponents and Radicals. And when we're talking about exponents and radicals, it's pretty much everything you learned in Algebra 2, particularly pre-AP Algebra 2. And then also we're going to go ahead and do 1.3, which is algebraic expressions, which for purposes of today's lesson is basically factoring, which we've already talked about a little bit in our trig unit. We're going to talk about it more on this lesson. Okay, so let's just go over some of the exponent rules. These are ones that you should know. However, you may have forgotten a couple of these, and I'm not going to do many examples. I'm really just mostly going to go over the rules. So like in particular, if I have a to the power of m, and I multiply that by a to the power of n, we call m and n exponents, and we call a the base. Since the base is the same, and since we're multiplying, this would be equivalent to the same base, which is a, to the power of m plus n. Now, you may be thinking that we should multiply it, but think of it this way. If I had a squared times a to the third, you wouldn't multiply 2 times 3. You would add 2 times 3 to get the total amount of a's that you're multiplying. Okay? The multiplying comes into play when you have a to the power of m and then that taken to the power of n. That would be like a to the m times itself n times. That's when you're going to multiply m times n. Okay? The next one I'm going to write kind of falls into the first rule. If you had a to the power of m divided by a to the power of n, okay, if you're dividing two expressions with the same base, you would subtract their exponents, m minus n. And this also has to do, and we'll write this one down here in just a second, has to do with the fact that a to the n power in the denominator, that's a negative exponent. Like I said, we'll get into that in a minute. Okay, let's say we had a product of two different bases. These could be numbers or variables. And you're taking that to the power of n. Okay, this is not necessarily distributing, but both of these things, even though I'm multiplying a times b, both of these have the power of n on them. A to the n, b to the n. And again, we're multiplying here. Okay, so this is important when you have a lot of things in parentheses and you're taking them to a power, everything has to be taken to that power. Okay. Likewise, if you have a divided by b, a quotient, to a power of n, then both things need to be taken to the power of n when you separate it. A to the n divided by b to the n. Okay, let's talk about, let's say you had a to the n times b to the n, and all of this was taken to the power of x. Okay, again, it's kind of like this rule. You would want to not really distribute, but it may help you to think of it that way, but it's not really distributing in the sense that we normally distribute. But both terms would need to be taken to the power of x, so this would be equivalent to a. Now remember, when you have power to another power, that's when you multiply the power. So here our power would become nx, and then times, you can either write times or you don't have to, and then b to the power of nx. Okay, a to the power of 0 is 1. Now this is going to work for anything, and I can say that. Now if a happens to be 0, there's a lot of debate over what this is. What is 0 to the power of 0? Is it 1 because of this rule? Is it 0 because 0 to anything is 0? The conversation to this is actually requires you to know limits, really, to be able to say it for sure. It's perfectly acceptable for, even if you think of a as 0, 0 to the power of 0, to say that that's 1. That's pretty much accepted in the math community, although technically it is undefined. But if you Google 0 to the 0 power, you'll find lots of interesting things, people debating with each other, and some of it you'll understand and some of it you won't, but you might find that interesting if you want to know more about it. Okay, let's talk about a to the power of negative n. All right, so here we have a negative exponent. So what does this mean? It means that I'm going to take the reciprocal of the base. So that would be 1 over a. And you can either put this all to the power of n, or you can just put the to the n in the denominator. Okay, it also follows, according to this, that 1 over a to the power of negative n is equivalent to a to the power of n. So regardless of which way you start, numerator or denominator, when you have a negative exponent, you are going to reciprocate the base, meaning numerator to denominator, denominator to numerator. Okay. One last thing having to do with that. A divided by b in parentheses, so this could be a fraction of numbers or variables, that taken to the power of a negative exponent would be equal to a numerator would become denominator, b the denominator would become the numerator, and then my exponent would just be n. Okay? All right, now let's talk about exponents and radicals. Okay? So when I say radical, you know, we have this word and we use it in math a lot, but really anything radical has to do with a root, not necessarily a square root, although that is kind of the default root. But let's say we had a to the power of 1 over n. Okay, this is the nth root of a. So the square root of a, n would be 2, and that would be to the power of 1/2. The cubed root of a would be to the power of 1/3. And all of this, regardless of whether you remember it or not from Algebra 2, you were definitely taught this in Algebra 2. And you're going to get to practice this in the assignment tomorrow. All right, let's say your power isn't as simple as 1 over n. Let's say you have a to the power of m over n. Well, in this case, this is like a really good rational exponent. I say rational exponent, rational meaning fraction, okay, or being able to write it as a ratio, and then exponent because it's an exponent. So this is rational exponent. And if I want to write this in radical form, I'm going to first just write my square root, and I'm going to write my a. M is the exponent. The numerator of this fraction is the exponent. So I'm still going to write a to the power of m. And then the denominator, like what we set up here, that's the root. Okay, so numerator is exponent, denominator is root. There's one other way to write this. It's only slightly different. It would be taking the nth root of a and then taking it to the exponent of m. And they're pretty much the same thing. I mean, they are the same thing, but it may depend if a was a particular number and n and m were particular numbers. One of them might be easier to compute than the other. Okay, let's talk about the nth root of a times the nth root of b. All right, so let's think about what this would be. This could be like the square root of a times the square root of b. If you're taking the same root here, then you can keep that same root, and that's ab. And this would go either way because these are equivalent statements. So you could break apart a root this way. Has to be the same root. Okay, this is like how we did with exponents. And going with that, if you had the nth root of a quotient, a divided by b, this would be equivalent to the nth root of a divided by the nth root of b. Okay, so those are your basic radical rules. I'm just going to do a couple of examples. Okay, let's say we had a number and our number was 4 to the power of 3/2. Okay, now this is something you could type in your calculator, obviously, but we're not going to do it that way. Okay, we're going to think about what these two numbers mean, and I'm going to rewrite this using this rule, actually, right here. Okay, we could write this as the square root of 4 cubed, and I could also write this as the square root of 4, I kind of wrote that weird, and then cubed. Okay, now one of these is much easier to compute than the other. Do you want to cube 4, which you may or may not remember, and then take the square root of that? Or do you want to take the square root of 4 and then cube it? And this should be a 4 here. Well, square root of 4 we know is 2, and 2 cubed is 8. Much easier to do it this way. If I had to do it this way, 4 cubed, that's 64. Square root of 64, still 8, but it was easier to do it this way. Okay, so some things to think about. I'm going to go ahead and move on to the next part, and then during the assignment, if you have other questions as to how to really work this out with numbers, we can do that then. You're going to have to probably brush up on your squares and your cubes, and we'll talk more about that in class as well. Okay, so now let's talk about simplifying. This is the start of the 1.3 algebraic expressions. Actually first let's simplify with some exponents. So the directions here are to simplify. This means you need to simplify all the way down that you can, and it also means that you should have no negative exponent in your final answer. If there's a negative exponent, then you didn't go far enough. Okay, so let's say we had 3x squared y to the 5th times negative 2x times y to the negative 8. And some people get confused here and they think, well, what goes with what? So over here it's pretty obvious that the 2 is the exponent on x and 5 is the exponent on y. But over here, some people might think, well, what does the negative 8, what is that the exponent of? It's just the exponent of the term immediately in front of it, which would be the y. So what would be the exponent on x? It'd be 1. And it might suit you all to go ahead and write that in. Okay, let's multiply, and let's start by multiplying the two numbers. 3 times negative 2. This is no rule. This is just math you've learned back in junior high, even before. So 3 times negative 2, that's negative 6. Okay, now I have an x squared, and I have an x to the 1. So I'm going to write x. Remember, we're multiplying these two things. So this goes back to the very first rule we wrote down. 2 plus 1, that's 3. Okay, or x cubed, which should make sense. Okay, now I have y. All right, so now I'm going to look at the y's. Y to the 5th, y to the negative 8. Add 5 plus negative 8, that's negative 3. And we're almost done, except I have a negative exponent. So what I need to do is I need to write this one more time. Negative 6x cubed over y cubed. Notice that I didn't move everything to the denominator, just the negative exponent term. And there we go. There's the answer. Okay, let's try another one. Let's say in parentheses, and sometimes we call this quantity 3x to the negative 2, y to the 4th, and then the quantity cubed. All right, so what we need to do here, if you remember, we just got to take each thing. So 3 cubed, that's 27. And again, it might do you well to kind of brush up on your squares and cubes, just the basic ones. And then for the power on x, okay, I need to take x to the negative 2, take it to the power of 3. So I'm multiplying negative 2 times 3, that's going to be negative 6. And then I need to do the same thing with the y. Y to the 4th cubed, 4 times 3, that's 12. And again, I have a negative exponent I need to deal with. So that x to the negative 6 becomes just x to the 6 in the denominator. So pretty easy to deal with. Okay, let's do, still simplifying, let's do a radical problem. Let's say we have square root of 18 plus the square root of 50. And I don't want a decimal answer here. That's not, I'm just wanting to simplify it. So this is something you should be able to do without a calculator. So we had talked last semester about how to simplify these. So I'm not going to spend a lot of time going over how to simplify these radicals. You can definitely ask me questions in class tomorrow, though, if you have them. So square root of 18 simplified would be 3 square root of 2. And square root of 50 simplified would be 5 square root of 2. Now, If these had been cubed roots, we would simplify differently. Again, this is something we're going to kind of work out, but square roots, we look for pairs. This is what you got. Okay, the whole point of this problem, though, is not to get from first to second step. That's something you should have already been able to do. Now we need to notice that we have 3 radical 2 plus 5 radical 2. Now what you might want to do is add 3 plus 5, and that's good. That's a good following your instinct. Now something else you might want to do is to add the 2's, and that's wrong. That is something that a lot of students want to do, but it's wrong. You need to just write root 2. Okay, now let me explain this to you. I'm not going to explain to you why it's not 4, but why it is root 2. Okay, imagine that instead of 3 root 2 plus 5 root 2, okay, so we're just kind of imagining, so I'm going to put this in a different color. Let's imagine you had 3x plus 5x. Okay, what is 3x plus 5x? Correct, it is 8x. It's not 8-2x, it's not 8x squared. When you have 3 of something and you add 5 of them to it, of the same thing, you have 8 of them. Okay, so that's why that did not change at all. Okay? All right. Let's move on to the next example. 2x cubed times the quantity of 5xy, all divided by 20xy squared. Okay, so we have a couple of ways to do this, but probably the way most of you are going to want to do this, and the way I'm going to work it out, is to go ahead and simplify the top. All right, so this is multiplication right here, so I'm going to go 2 times 5, and that's 10. And if there had been an exponent up here, I would have had to deal with that first before I multiplied. Still following PEMDAS. All right, x cubed times another x, that's x to the 4th, and then a y. Okay, divided by 20xy squared. All right, now 10 divided by 20. This is just standard arithmetic. That is 1/2. So I'm just going to go ahead and put a 2 in the denominator. And I do need to put a 1 here if everything's gone. But if something else is left in the numerator, you don't have to put the 1. But if everything did actually move to the denominator, you'd still have a 1 up here. But that's not going to happen in this case because x to the 4th divided by x, remember we're dividing here, so the exponent on x would be 4 minus 1, which is 3, and since that's a positive number, I'm going to put it in the numerator. All right, now when we're doing y divided by y squared, you know this, you could almost think of this as being bottom heavy. You know that it's going to go down here. You could think of it as 1 minus 2 is negative 1, so just y to the 1 is going to be in the denominator. All right, and that's it on that problem. Okay, let's just do a couple more of these, and we'll move on to factoring. Okay, so I already worked one kind of like this. Let's see if you remember what I said. 8 to the power of 5/3. Now, you are going to get an integer here. You're not going to get a radical or anything weird, a decimal, and this is going to be something that you should be able to find pretty easily. Now, hopefully you remember what I said, and that is the bottom number is the root, the top number is the exponent. Now you can either put the exponent here on the right next to the 8, or you can put it on the outside. Now I'm putting it on the outside because it is much easier to cube root 8 than to cube root 8 to the 5th, which I don't even know what that is. But cube rooting 8, that's simple, that's 2. Okay, now let me explain to you how I got that in case you don't remember. Let's say we have cube root of 8. Now if I break up 8 into 2 times 4, and I break up 4 into 2 times 2, what you're looking for are pairs, but are groups of 3. So I have one group of 3 2's, and then there was nothing left over. If there had been something left over, I would have written it. But if you know that 2 cubed is 8, then this was even simpler than that. All right, now I need to do 2 to the 5th. Now you may not have this memorized, although it is something today you should try to commit to memory because it comes up a lot. But I already know that 2 cubed was 8. Okay, so really I just need to multiply by 2 more times, or by 4. So you get 32. You could also think of it as 2 times 2 times 2 times 2 times 2. Now some of you, just by the fact that I just said that, are thinking, well, there was an easier way to do this in the very beginning. Since 5/3 was an improper fraction, you could have actually written this as 8 to the power, this is kind of going back, 8 to the power of 1 2/3. Okay, and some of you are going to think this is harder than the way you just did it, but some people really like this. So think about 1 2/3. This is like 1 plus 2/3. And this could keep your numbers down in another problem. Okay, so this would be like 8 to the power of 1 times 8 to the power of 2/3. And then if you think finding 8 to the 2/3 is easy, then all you got to do is multiply by 8. Let me kind of work down here. So this is just 8, and this is the cubed root of 8, and then squared. Well, we just said the cubed root of 8 is 2, so we have 8 times 2 squared. Now in this particular case, I think the way I did it first was easier, but in some problems, as the numbers get larger, and if you don't have a calculator, this is not a bad way to do the problem. Okay, last simplifying one. Let's say we have negative 27 to the negative 2/3. Now, before I continue, I'm not even going to let you try to make a mistake that many students would make. This negative right here in the beginning is not taken to this power, and that may or might not make a difference. In this case, it would, though. Okay, if I wanted this to be negative 27 to the negative 2/3, I would write parentheses around negative 27, but there are no parentheses. So this negative is not securely attached to the 27. It's like a negative 1 times 27 to the negative 2/3. Remember PEMDAS. You are going to do the exponent before you multiply by negative 1. Okay? So really this is like this. All right. So let's think about what this is. So this is like negative. I'm going to go ahead and take care of this negative that's in the exponent. And then this negative can stay out to the side. It can go up with the 1. Either way, it's the same thing. So negative 1 over, and then the bottom number 3, that's the root. So it's the cubed root of 27. And I don't want to square 27. So put the exponent outside of the root. Okay, so again, I have negative 27. The cubed root of 27, that's 3. This is something we should know. And then square it. And that gives you negative 1/9. Now, if you didn't know that the cubed root of 27 was 3, then you would need to go off to the side. You would need to break 27 up into 3 and 9. 9 breaks up into 3 and 3, and you can see that 27 is 3 cubed, so the cubed root of 27 is 3. Okay, now let's talk about factoring. Okay, let's say we have x squared plus 2x minus 15. We're just going to start off with something simple. Hadn't been in school very long, back from the break. This is something you should be able to do. Now, since the leading coefficient is 1 here, all you're doing is thinking about, okay, what is the factor pair out of negative 15 that adds to positive 2? So this is, we think it's going to be 3 and 5. I'm going to go ahead and write that. We need to decide which one needs to be negative. I'll say negative 3, 5. You do not have to do grouping here. When you have a leading coefficient of 1, grouping is way overkill. All right, that's how you did it when you first learned. We're past that. Okay, that was like Algebra 1. In pre-cal, you should be able to go straight into the 2 factors. So x minus 3, x plus 5. Now, if you don't feel confident in this, just do a quick distribution. X times x, x squared. Outside would be 5x, inside would be negative 3x. That adds to 2x. Negative 3 times 5, that's negative 15. You're done. If the leading coefficient, though, is something other than 1, you would probably want to do grouping, okay, which I did review last semester, and we'll probably get to 1 before this lesson's over. All right, let's talk about a special one, a squared minus 16. And again, we reviewed this last semester, but this is a difference of squares, okay? Essentially, what you're doing here is you're saying, what's the factor pair of negative 16? That adds to 0. Which would be 4 and negative 4, or you put the negative 4 first, it doesn't matter. So this becomes a minus 4 and a plus 4. Or you may have memorized something like a plus b, a minus b back in Algebra 2, but at this point, these two should be really easy, all right? All right, let's step it up just a little bit. Let's say you had 15a cubed b squared minus 25 a to the 5th b to the 4th plus 35 a squared b to the 4th. Now if you remember something, and I hadn't talked about it yet this lesson, but you would always want to look for least common denominator. This is your first step, always on factoring. Okay, so let's first just look at the numbers. 15, 25, 35. What's the least common denominator? Or sorry, I keep saying least common denominator. I apologize. What is the greatest common factor? What is the largest number that evenly divides into 15, 25, and 35? That would be 5. Okay, that's not that hard to find. When you're doing this with the variables, though, what you're really looking for is the smallest exponent, because that's something that will go into everything. So you wouldn't want to pick a to the 5th, even though that's the greatest one. That doesn't, I can't pull an a to the 5th out of a squared. So you're actually looking for the smallest exponent there. So that's a squared. So then what would it be for b? We got b squared, b to the 4th, and b to the 4th. All right, so that would be b squared as well. All right, and then you're going to open parentheses, and you're going to write what's left. And when I say factor out, I might as well be saying divide out. So 15 divided by 5, that's 3. A cubed divided by a squared, that's a. And essentially what you're doing here is subtracting, because that's what you do when you divide exponents. B squared divided by b squared, you took everything out, that's a 1. Not b to the 1, but a true one, so we end there. And there's a really easy way to check your work here. So if you make a mistake, you should be able to fix it. All right, minus 25 divided by 5, that's 5. If I factor out a squared from a to the 5th, I'm left with a cubed. And if I factor out b squared from b to the 4th, I'm left with b squared. All right, plus. So hopefully you're getting the hang of this by now. Now, if you have, like here, I didn't say it, but when you factor out a squared from a squared, factor out everything, you're done. Now, at this point, you would want to look at this trinomial and think about, could you factor it? The numbers don't work here, but even so, the variables don't work. All right? So it is possible that this is all you could do. All right, let's try one that's a little bit weirder. 3x to the 3/2 minus 9x to the 1/2 plus 6x to the negative 1/2. Now, when you're factoring out a GCF, which hopefully you picked up on the fact that they all have an x, we can't just do an x, okay? It's like what I said on this problem. What you're looking for is the lowest exponent, the least number, which in this case is x to the negative 1/2. Now, don't skip over the 3, 9, and 6, because you can also factor out a 3. But the exponent on x has to be the smallest exponent, which in this case is negative 1/2. Now we got to figure out how to deal with this. So I factor out a 3 from 3. Okay, that's done. 1 is left. You know, when we could write that, but we don't have to on this one. And then to find what the power is on x, instead of thinking as dividing, just think, what is 3/2 minus negative 1/2? And I'm going to actually write it here because I want you to see what happens. 3/2 minus negative 1/2. That's like plus 1/2, which is 4/2, which is 2. Okay, and then minus 9 divided by 3, that's 3. And to find the power on x, I'm going to do the same thing over here. And once you get comfortable with this, you probably won't have to write it out. If you're going too quickly here, you might think, oh, 1/2 minus 1/2, that's 0. But it's not. It's 1/2 minus negative 1/2. That's like plus. That's 2/2, which is 1. Or I'll just leave it as the way it is. All right, plus 6 divided by 3 is 2. And then I factored all of the x negative 1/2. And so I don't have to write anything else. And then this trinomial is something that you can factor. Okay, so thinking about this, we have 2. I have negative 1 and negative 2 adding up to negative 3. Because the leading coefficient is 1, I don't really need to do anything else except write my factors. And then the very last thing you would want to do is follow that simplification rule, which is put that negative exponent in the denominator. This is not one of those rules that's always followed. Sorry, let me back up. I got too busy talking. The 3 should stay in the numerator, but this moving x to the 1/2 in the denominator, and I keep talking, I'm sorry, x to the 1/2. This right here is not something that's always followed. It's kind of like simplifying radicals in the denominator. There will be a time when leaving negative exponents is fine, but for right now, let's just always simplify it so that we've practiced it. Okay? That is your final, most simplified answer, although this would be accepted most of the time in later classes. Okay. All right, let's see. We have x plus y, the quantity, squared, plus 2 times the quantity of x plus y, minus 3. This brings back something I talked about before, which is u substitution, where we said let u be some term that's repeated. In this case, it's not a sine or cosine, it's x plus y. Now, it's not necessary to solve this problem, but it does make the next step much easier. I can see now that this is definitely factorable. If I break up negative 3 into 1 and 3, where the 1 is negative, negative 1 plus 3 is positive 2, so this factors into u minus 1 and then u plus 3. It's probably easier to see it this way than it was in its original form. The only thing you've got to remember with u substitution is you've got to substitute it back at the end. A u was not part of my original problem, so it can't be part of my final answer. Oops. Plus x plus y plus 3. So you don't have to do u substitution to factor this, but it does make it easier to see. Okay. Number 12. Let's say we have 3 parentheses 2x minus 1 squared, and then I put a 2 here, which may seem a little random, but there's reasons why we're writing it this way. This is the way a lot of time after substitution you will see it in calculus. It just means multiply. So let's incorporate some of the things we've learned into this new problem. This is another one where you could be using u substitution, although you'd kind of be using it in a couple of different places. So I'm going to go ahead and do this one without. And remember that we're factoring here. One thing that may be beneficial is to go ahead and just get one leading coefficient. Like rewriting this as 6, 2x minus 1 squared, x plus 3 to the 1/2, and then 1/2 if you're good juggling a whole bunch of numbers, this may not be necessary. But if you get confused easily, then I suggest you do this. Okay, so now let's talk about it. Between 6 and 1/2, you may be thinking there is no GCF that I need to take care of. And I'm going to just kind of ask you to go with me on this one, and I'll show you kind of why it works. I'm going to factor out a 1/2. The reason I'm going to do that is because then at the very end I can just have a 2 in the denominator. But if you factor out a 1/2, and like I said, I just asked you to kind of go with me on this, then that's going to make that 6 of 12. I'm kind of getting ahead of myself though. Alright, so that's the GCF between 6 and 1/2. Alright, now let's figure out what the power should be on 2x minus 1. Alright, I have a 2 and I have a 3. When you're talking about GCF, you always pick the lower power. Alright, so then what would be the power on x plus 3? 1/2 or negative 1/2? You'd pick the lower number, negative 1/2. Now all of that was just to pick out the GCF. Now we need to figure out what's left of these two terms. So again, what's 6 divided by 1/2? That's like 6 times 2, so that's 12. And now thinking back to factoring out, you can either subtract the two exponents or think about what's left. In the 2x minus 1 case on the first term, nothing's left. Okay, or you could say a placeholder 1 is left. All right, not a power of 1, but just a true 1. So I'm going to go straight to the x plus 3. To figure out the new power, you need to think not 1/2 minus 1/2, but minus negative 1/2. Well, that's like 1/2 plus 1/2, which is a 1. All right, plus. Now remember our GCF was a 1/2, and I factored that out, so I'm done with that. All right, what about the power on 2x minus 1? Okay, it was cubed. I factored out 2 of them, so to speak, so you're left with a 1 there. And then in this case, the x plus 3 has gone away. All right, now because I made this 1/2 my GCF, I no longer have a fraction that I'm going to have to distribute through and then deal with more fractions. Here I just have one fraction. That's why I did that. So let me rewrite this first term. And let's distribute through here and simplify, and then maybe we can even continue to factor. So that would be 12x plus 36. This would be plus 2x minus 1. And if I had not factored out the 1/2, I would be having a fraction there, which is hard to deal with. Okay, so let's keep going. At this point, we're more or less simplifying. We're kind of done factoring. So 12x plus 2x, that's 14x. And then 36 minus 1, that's 35. All right, do you see a place where we can factor this further? In this case, yes, there is a 7 that I can factor out. So when I factor out a 7, I'm just going to go ahead and move it to the top, and that's going to give me 7/2. This term is going to stay. And sometimes you can kind of predict this is going to happen, but in this case, there really was no predicting. So if I factor out a 7, I'm left with 2x plus 5. Now this is not a bad answer. The only thing I'm going to do is kind of make it look nicer. And mainly, I'm going to move this x plus 3 to the denominator. And in doing so, in creating a fraction, I'm going to put the 7 as the numerator's leading coefficient and the 2 as the denominator's leading coefficient. This is going to make it look nicer. Okay, this x plus 3 goes to the denominator, and that becomes just a positive 1/2 once you move it, and then 2x plus 5. Now you may be thinking, man, this is an awful lot of work, but I got to tell you, as far as graphs and asymptotes and end behavior, this final thing was a lot easier to read than the first thing. And we will get to all of that, but right now we're just practicing factoring. Okay, last problem. I know these are long notes, so Just hang in there for one more problem. So x to the 1/2 minus 7x to the 1/4 minus 10. I'm sorry, plus 10. You may be thinking you cannot factor it, or I don't know how to factor it. Or you may be thinking it's trinomial, but I'm not really sure what to do next. If I let, and in this first one, again, I just want you to go with me on this. If I let u be x to the 1/4, I picked this one for a reason. What would x to the 1/2 be? Okay, that would be u squared. If you think about it, if I squared both sides, 1/4 times 2, that's 1/2. And these are generally going to work out just like that. So this becomes u squared minus 7u plus 10. Well, that factors nicely because the factors of 10 are 5 and 2, and we want them to be negative so that they will add to negative 7. So that becomes u minus 5, and this becomes u minus 2. This is all nice, but I didn't have a u in my original problem, so I got to go back. X to the 1/2 minus 5, x to the 1/2 minus 2. And as crazy as that looks, that is the final answer on the factoring. One thing I didn't mention as we went along, because sometimes it's more problem, or it's crazier than it looks, and I just realized I made a mistake because I'm trying to wrap up too soon. Some of you might have caught this. Those should not be 1/2, those should be 1/4. You can always check factoring by multiplying out your answer and seeing if it is what you started with. Now, in this case, it's maybe not that bad. In the last problem, this would be kind of crazy to do. In the beginning problems, though, especially these, very easy to check it in that way, okay? But that's really not a foolproof way to do the problem. A lot of times, people end up making the same mistake. So if you're going through this assignment, I highly encourage you to check your answers on the odds with the ones in the back of the book. Okay, bring your questions to class.